P, right? Because we will take the case of a neutral equilibrium, I can write P to be equal to PCR, right? So this is my PCR. So PCR into delta minus Y by EI, and this moment is essentially, if I take an element at this point, PCR into delta minus Y will apply some sort of a clockwise moment, and to restore it, the bending moment will be like this. So effectively the bending pattern of this element will be like this, and it corresponds to a case of a hogging moment. So it will be negative minus Y double dash. Now if I bring this Y double dash on this side, I will have Y double dash plus PCR into Y by EI is equal to PCR delta by EI. Now this corresponds to my my differential equation Y double dash plus K square Y plus K square delta. And if I can have the solution to this thing as Y1 is equal to, one solution will be A sine Kx plus B cos Kx. This will be my first solution. Now Y2 will be effectively delta, and Y1 plus Y2 is equal to Y will be equal to A sine Kx plus B cos Kx. Any problem in understanding this step, one should go back to the things of differential equation, right? Plus delta. So dy by dx is essentially equal to A k cos Kx minus B k sin Kx. So essentially this is my number 2 equation and this is my number 3 equation, right? Now let us put the boundary conditions in, right? The two boundary conditions are effectively, I should say there are three boundary conditions here. The first boundary condition, when x is equal to 0, y is equal to 0. And I place this in the number 2 equation. If I place this in the number 2 equation, I have 0, a sin kx is equal to 0, b plus delta. Or effectively, what I have is b is equal to minus delta. This is number 4. Now also, as this is some kind of a fixed end, therefore at x is equal to 0, I also have y dash to be equal to 0. Or effectively, this is 0, this thing is equal to ak, and this is effectively equal to, I think this one is equal to ak cos kx here, and this one is equal to bk sin kx, which is equal to 0. So a is equal to 0. Right. So we can substitute 4 and 5 in 2. What I have basically is that this a is effectively 0, so I can cancel this term. This b, I can substitute this by minus delta. So what I have is y is equal to delta 1 minus cos kx. So this is the equation of the elastic curve with amplitude of delta. Right. Now I will rub this out now. Now at x is equal to L, one will have y to be equal to delta. So effectively delta is equal to delta 1 minus cos kl, or delta cos kl is equal to 0. This can happen in two cases, either delta to be equal to 0 or cos kl to be equal to 0. Now this case corresponds to the case of a stable vertical configuration, or a vertical stable configuration wherein the load P, right, will be lesser than PCR and the column will revert back to its original configuration. So here delta will be equal to 0 and this condition of the elastic line will be satisfied. No props. So the next thing that we are going to do is, if cos KL is equal to 0, what it effectively means is that KL is equal to nothing but n pi by 2. Now this K is equal to root over PCR by EI n pi by 2, or I should say PCR, or the critical load, is equal to n squared pi squared EI by L squared. Now obviously the critical load will be at the minimum value of this, and to get the minimum value of this, what I need to do, it will be 4L squared, I'm sorry. And what I need to do is basically plus n to be equal to 1, right? So it effectively is that PCR is equal to pi squared EI by 4L squared. Now all these things, some sort of a mathematical calculations and all these things. So effectively the thing is like this, that I have a vertical stable column, right? I place a load P, right? I give it some sort of a lateral deflection, suppose delta. Now if P is lesser than PCR, the column will revert back to its original configuration. Now I got to find this value of PCR at which it will maintain a stable neutral equilibrium, right? And this corresponds to the equation of this elastic line. And I put the boundary conditions in and effectively find out the value of PCR, which is my Euler critical load. Now a study of this Euler critical load, or PCR, I should write it big. Now PCR effectively, or the Euler critical load for this is PCR is equal to pi squared, which is a constant, EI, which is the flexural rigidity, by 4L squared. Now from this equation, it's pretty clear that while designing column, we got to play with PCR, right? Because effectively the column will fail by buckling. And effectively what I need to do is that I need to place in loads which will be lesser than PCR. So I need to play on with this value. And for playing on with this value, effectively I have got two factors. Number one, this EI, and number two, this length. Right. And essentially we see from this equation that the compressive strength of the material by which we are building the column is essentially not important. Like in case of a strut, it was pretty important because the strut didn't fail by buckling. The strut failed when the compressive stress of the strut exceeded the compressive strength. But effectively here, the column fails by buckling. So effectively this critical load is pretty important, and the critical load, the factors on which this critical load depends are not the compressive strength essentially, but the flexural rigidity and the length of the column. Right. Now this flexural rigidity is governed by EI. Right. And what is this EI? E is the Young's modulus, and I is effectively the second moment of area, or the moment of inertia. And effectively if the EI, if the flexural rigidity increases, that effectively means that the Euler critical load will be higher. That is, the column can take in a higher load. Because what is EI effectively? EI effectively represents the column's resistance to buckling. So if the column is more resistant to buckling, so obviously it will take in critical load, right, greater. So obviously it will take, I should say, the load, greater load, right. Now the next thing is playing with the value of L. If I have shorter kind of columns, then obviously the PCR value will be greater. So for a shorter column, I will have greater PCR, and for a greater flexural rigidity or greater EI, and I can be effectively increased by placing the material as far apart from the two principal axes as possible. I can increase the value of PCR.